Well, welcome everybody. I'm Dale Cronkright. My contact information is up there. Feel free to copy down. If you want to direct any questions to any of our panelists today, just contact me and I'm happy to send you their contact information. This session is about quantitative imaging in art preservation and art conservation in museums. And it really is about taking what has been an illustrative medium, a documentation medium of photography, where we record previous conditions, we record technology and fabrication, characteristics that we then look at as a photographic image and try and interpret from, and move it one step beyond that to using the digital image capture system as a way to actually gather measurable data and then manipulate that data and allow us to measure change over time. So briefly, just let me tell you how it is that I as a conservator became interested in this subject, and that'll set the stage. Conservators are all about managing change. We never stop change, of course. That's an impossible thing. But if we know the rate of deterioration of an object under our care, we try and do things that will slow that rate of deterioration and give it as long a life as possible. So this is an RTI HSH 3D image of a painting by George O'Keeffe, and we're going to sort of briefly zoom in on that painting right now. Because you can see that it shows paint textures extraordinarily well. It shows cracks and damages extraordinarily well. It allows us to light it dynamically as well as zoom in and see lots of characteristics. But as I got closer and closer, what I began to see in the surface, besides the weave texture of the canvas, were these very small micro protrusions. And these very small micro protrusions, as it turns out, that are emerging from O'Keeffe paintings. And I'll just quickly point to a couple of them here. Good. Right? You can see these high micro protrusions most easily right in here, right in here. There's a group in here. There's a few in there. Those micro protrusions are lead soaps that are eating their way through the fatty acid and fatty acid esters by forming lead hydroxide every time water molecules move through that paint film. And what I thought to myself is, boy, this is the first time I've ever been able to image those micro protrusions really, really well. I can almost map them. And then it came to me, boy, if I could take a photograph now, put that piece in a micro-environmentally controlled frame where humidity should be stable, and then check it again in 5 years, I could actually measure whether I was successful in slowing the rate of growth of the micro protrusions. And that idea of conservators being able to check whether their work and their techniques actually slow the rate of deterioration is what made me really interested in quantitative imaging. That is, using it to establish the rate of deterioration and quantify whether we're having an impact in slowing that rate of deterioration. So what we'd like to do in this presentation today is obviously introduce you to the steps that these four researchers and their teams have been taking to advance quantitative imaging, because there are a lot of technical problems. Try to identify those technical obstacles that are right now preventing conservators and museums from broadly adopting quantitative imaging as a documentation technique, and the cultural obstacles within museums that might slow integration of this technology into our preservation workflows. Because obviously, if it's technically difficult, if you have to do a lot of fussing, if the user interface is difficult, many conservators simply will not be able to take the time. They are so compressed for time. So we need to be able to save time and increase their workflows. We'd like to ignite a discussion with you about what you think might be some rapidly viable research projects that can overcome some of the obstacles that we identify in today's talk. And then finally, we would like to entice all of you to join us and become collaborators in the development of these preservation tools. So if you see an area you're interested in, if there's a project you think you might want to be able to collect data sets on and help us advance it, we'd love to have you join us. Right off the bat, the question is, well, what do you mean by quantitative imaging? Okay? Quantitative imaging, the way we're using it today, is that digital imaging technologies, both the capture technologies and the processing technologies, that are comprised of numerical values and which relate to calibration standards for which accuracy, precision, and noise can be quantified. So the idea here is that the measurements are accurate. That is, that the measurement you get with the imaging technique of 5 centimeters actually represents true 5 centimeters of ground truth in any way, or any function of that. And that the variation of the instrument, the sensitivity of the instrument, is quantified, so that we know any measurement below the sensitivity of the instrument is just noise or variation, but that values above the variation may very well be quantitative change in condition, or whatever factor you're trying to measure with quantitative imaging. So accuracy, again, precision, variation, and calibration are the keys to moving qualitative imaging into the quantitative sphere and allowing us to actually have measurements that we can save, that we can use, that we can record true physical states of works of art, artifacts, and buildings, and measure rates of deterioration over time using these techniques. What are some of the obstacles? Well, obviously variations in capture conditions between one time and 5 years later, calibration standards that you're using in the capture, the instrument sensitivity changing over time, one camera versus another camera 5 years later, registration and alignment between the measurements made of serial photographs of the same object. Each of these can have an effect on how quantitative the measurements obviously are. So illumination source and visible lighting, you have to know the color calibration of your illumination source if you're really going to know what that RGB data is giving you. Too much resolution is sometimes a bad thing. In a very dense point cloud, whether it's from a laser scan or from infrared, something will have always change. Objects move all the time with subtle changes in humidity and temperature and air. So some things are always changing, and if your resolution is too tight, if your data points are too tight, you will always see change. And that's a bad thing, because what we're really interested in is changes that are meaningful, that represent a change in condition. Speckle effects in laser scanning, so changes in humidity, dust, these are the things that during different capture sequences can affect the accuracy of the measurements. And in photogrammetry software, there's an optimization where the software reads your CPU and your GPU speed and capability and decides how many points to use in putting together the mesh in a reasonable amount of time. So you can use 2 different computers with 2 different CPU and GPU units that will give you different meshes. And if you're trying to measure them metrologically, that's really going to show you change that hasn't taken place. So you need to make sure in digital imaging that you're capturing good archival quality stills in raw format, saving them as DNGs. Those are your archival forms. And then when you're putting together a photographic mesh, you're using those, putting those together and processing all your meshes using the same CPU unit. Just an example of some of the problems. So right off the bat, and then of course, we're doing this in a museum, so these digital records need to be archival, right? We want them to last for a very long time. We want to be able to search with them, share them, and pull them up in the future. So we need to protect against digital file deterioration. So we need to attach checksum hash values that will detect changes, deterioration, accidental corruption of those digital files. So that if we use those to compare to an image we take 5 years later, we know that we have good uncorrupted file data or perhaps some corrupted file data. We need to be able to archive them so that regardless of operating system and software version, so we really need to use as much as we can non-proprietary open file formats. And our metadata is critical for saving, indexing, and retrieving and sharing this information. That's an introduction of quantitative imaging, the way we're going to talk about it. I'm going to turn it over to Greg Berman, who is a physicist, formerly of the Jet Propulsion Lab in Pasadena. Greg's been doing a lot of work with multispectral imaging as well as reflectance transformation imaging, and he's going to talk about his approach to quantitative imaging to measure change in cultural heritage materials.
Well, as the title says, it's quantitative imaging. So how do you go from what is pretty pictures, very arresting visualization to numbers that you can turn a computational crank on that will give you something that you can look at over a time series. Because that's really what we're interested in. We're interested in getting data sets that are quantitative enough, and so that you can look at something in January and June and January and June again to meet what Dale wants, was to look for changes for that. So my experience of this comes from the Leon Levy Digital Dead Sea Scroll Library. And the Israel Antiquities Authorities has been re-imaging all of the Dead Sea Scrolls and putting them up online, and I am the imaging and technology consultant and advisor for that project. And a lot of this experience I'm going to talk about came out of that, because really the motivation behind that particular project is, everybody wants to see the pictures of the scrolls, but underneath it is the fact that they wanted us to develop a means for monitoring them for a conservation project. They just wanted to know what's going on with them. And what we decided to do was to use spectral imaging to look at the surface reflectance. And the reason for that is that that's the known driver for changes. I mean, I'll skip all that, there's tons of slides on it, but we know from work that I did about 20 years ago that this is what makes a lot of ancient texts change from legible to illegible is surface effects. So the idea behind all this is that I always say January and June. This is like Alice and Ted and Bob if you do cryptography. So this is kind of the way this is my language. And so, as I said, what you want to be able to do is compare these things over time. You want to have quantitative values, and the burden on imaging is really quantitation and reproducibility. I'll talk about that a little later on. But this is really what drives it. Otherwise, you can't really compare things. And the other thing is, it was clear very early on that if you're going to have an image-based methodology, you really need an image-based algorithmic method for looking at the data. You can't do this by eye. You need something that you need to define change. You need to find software that trundles through all the images and computes it for you and flags it and has a visualization engine behind it that the conservators can use. So the key for all this is, to paraphrase real estate, calibration, calibration, calibration. And I have harder reading these things. The issue here is precision versus accuracy. And if you think about what you want to do, where you want to be able to compare data reliably over a time series, what you're really interested is in precision. And so you can live with systematic errors, you can live with offset as long as you know what they are and as long as they're reproducible, because that's really what you're doing. It's nice to get accuracy, which is in the case of spectral imaging that you can compare with known standards. That's great. And you can't be terribly wrong. But on the other hand, the fact that there's a systematic shift in, say, reflectance isn't a killer for this thing. The big effort for us was to make it reproducible rather than absolute, quantitatively absolute. And let me see here. So the way we're doing this is we did a couple things. I'm going to try to give you the big picture. The big picture is basically there's a lot of things that you have to worry about. You have to worry about the lighting. You have to worry about illumination gradients across the field of view. You have to worry about camera jitter. There's a whole bunch of stuff that goes into this. And the idea really is to calibrate all this out using targets, and particularly in the field of view. The way we have the system set up, there are spectral and color targets in every single image, and if need be, we can go back and back out the data for any single image if we have to. So you want to have these files all kind of self-referential, because things drift. So if things begin to drift a little bit, you want to be able to go back and pull that back out of the image and correct it. And what we're doing now, for example, one of the lessons learned is that you have the system, and we spend a lot of time calibrating it, and then you say, we take it to Jerusalem and we install it, and then you say, okay, well, the people running it aren't the people that built it and calibrated it, right? Because you've delivered it to somebody, and they're using it on a daily basis. And so you need to come back in and take weekly and monthly calibration data. And as I said here, once you have all this data, boy, you can't let it pile up, we discovered, because it's a lot of stuff to trundle through. So from an operational standpoint, if you say to yourself, well, I'm going to look at an object over a long period of time, you also need to look at the calibration of the system as you go along. And we've actually had a few hiccups where we watched the data, we saw something change, and we had to recalibrate data after that. But if you have all the calibration standards in the field of view and you do the calibration regularly, it's a pain, but the data's all there. You haven't lost anything. And like I said, now for the scrolls, since we're looking at spectra and color, there are NIST traceable spectral and color standards that we're able to buy and to use. And we also measured those separately as well as using the vendor information. And like I said, do not get behind with the tracking data. It was a mistake to let that happen. So when you think about this thing and you say, well, okay, what I'm interested in is reproducibility. So the way we decided to approach this was to develop statistical measures for the system performance, the system reproducibility. And because that ultimately sets how good a job you can do. If you have a system that's measuring reflectance, which is what we're doing, and all the values are, we normalize it, it's all absolute reflectance between 0 and 1, and if your system reproducibility is 0.5, well, that's not a very good system for measuring change. So the first thing that we spent a lot of time on was measuring the reproducibility and what we call variability. You can call it noise, which is just everything kind of lumped in at once. You can get a little semantically confused, as we did at lunch. But you need to do that so you really understand the system. And I gave you the value that we have here. This is what we got for our system. So the reflectance, we were measuring at the plus or minus 0.02, which is actually pretty good radiometry. Actually, the system actually is better than that, but for reasons that aren't worth going into, it turned out the standards actually weren't as good as the system. So you need to set that threshold, because what's going to happen is when you come back in June and you want to measure something, you have to say, well, how do I know if it's different than it was before? And the answer is you have to develop some statistical measure and say it's 1 sigma, 2 sigma, 3 sigma, whatever you think is probably at least 3. And that's the measurement that we did. The way we actually did the measurement was let me skip this here. I want to go this. No, we'll go this one. So I'm going to kind of skip over it, but we use multivariate analysis to sort of collapse the spectra down. We didn't look at individual spectra. We used techniques that we took from control theory and statistical process control that, say, the pharmaceutical companies use for their quality control. So there's a well-developed statistical method that we borrowed, but applied it to these images and to spectral measurements. And it's all in our papers if you want to read them. But the big issue for imaging, and we're going to talk about it with the RTI, and John, I think, will talk about it a little bit, is image registration. Because you're measuring something in June, you're measuring something in January, and you can't get them in the exact same spot each time, so you have to worry about how to do the image registration. And what we found out for the scrolls was, there's two things, right? There's rigid body, and then there's elastic deformations, rubber sheeting it. And the scrolls are on parchment, and the parchment itself responds to the environment. So you can take it out, and it can be slightly different shape. It'll curl up. You can actually see this do that when you take parchment when you take a scroll out of the vault, and even if you walk it across the room, the hall to the imaging lab, which is the same environment as the vault that they're normally kept in, you can still watch it kind of creep up a little bit and move. So what we decided to do, what we found out was that unless we allowed for elastic deformations, we couldn't really get a good image registration out of this. And let's see here, where's this? There we go. So it really turned out that the largest source of error, which in this case is false positives, turned out to be image registration. And it turned out that in fact you could do such a good job on measuring the reproducibility and the variability that when you tried to register them, there was enough misregistration that every pixel said, oh, I have changed. Because if you're using spectroscopy and you're looking at the spectrum of a pixel in January and June, if you have the pixel misregistered, then the pixel next door is different. So it will always think it's different. So that was we just got a massive, the whole thing went crazy. So there was it was a surprise for this particular project.
It said everything had changed, but everything hadn't changed.
No, and the way we knew this, it was just sequentially taken data. So as a result, the data was 5 minutes apart, so really nothing had happened to it in the meantime. But you would see these kinds of effects. And this
How
is.
do you register?
Hmm?
How do you register?
We used SIFT to locate points, and then used actually it was a routine from ImageJ, which does rigid body. It does the elastic, and you can just watch it go.
Well, presumably you have to set some sort of radius for which it's searching for the change. So if you set that too low, match every pixel to the closest pixel nearby, and you get false negative.
Well, that's right. Yeah, it can go both ways. So when
So
you
there's some sort of feedback to the physics of the object itself that you determine how much it can physically move within some frame of physical reference, or you just gut feeling how large that radius had to be based on the results.
Let's see. Let me see if I understand the question right.
No, we're just saying set some sort of parameter so that.
Well, no, the image registration wound up to around a pixel or so, and the solution to reduce the binning, the approach was to damp down the effects of registration, and then let the true nature, the true variance of the system spectral measurement drive whether a pixel had changed or not, was simply to bin it. So if you bin it by n, you reduced a misregistered pixel, and that superpixel is down by 1 over n squared. So that was the effect, and we haven't published this yet, but you can just watch the false rate error just drop right off as you increase pixel, the binning. And actually, it's interesting. You can see it. It's most important at the edges of text, because you have a misregistered ink pixel and a parchment pixel. That's where the greatest spectral change is. You don't really see it much on, say, in the middle of just a piece of parchment, because a piece of parchment is very similar to one that's a pixel over.
Except that where you would have the greatest change, pardon me, is also where the defects in the lens are at their maximum. Right? I mean, going from a black ink to the white parchment or a beige parchment, that change in contrast, depending on the lens you use, you're going to get into more barrel distortion on the lens, aren't you?
No, this is an extraordinarily good lens. This is a custom design lens. But yes, you're true. But remember, my before is taken with the same lens, so actually it doesn't make any difference, right? Because I developed my before. I use the same lens, the same system, and the fragment isn't just kind of willy-nilly thrown down. We put it in about the same spot, so that if there was barrel and lens, I can send you the lens spec. It's a great lens.
But you do have to worry about phase sampling. So if your point spread function is much smaller than your pixel, then you can shift these edges, and so you'll get.
Yes,
so this is sampling part of the problem that kicks in, which is another way to distortion.
Well, I mean, focusing on the cone of the CCD, right? Also, I mean, it's like you just an incremental change in the shift where the camera is. So that pixel, I mean, the cone, if you're.
No, I mean,
Yeah,
well.
I'm going to.
Well, no, we're talking about no. Okay, but I mean, the camera's fixed.
Yeah.
Okay. One of the advantages of this particular system, it's a very well funded project. It's in its own room. The camera is bolted to the ceiling. The copy stand's bolted to the table. The table's bolted to the floor. The lights are bolted to the ceiling. So nothing's moving it. So it was that was a that makes some of the issues that come up when you bring a system in and set it up and take it down. But I have an answer for that one. I'll show you. I can show you some data afterwards where we did just that.
But so your registration correction method was more of just binning out to a lower resolution or a super pixel rather than some form of mesh adaptation, some sort.
Well, no, the elastic deformation is local. In other words, it's the elastic deformation by its nature. You know, it lets it deform locally a little bit to do between.
That's prior to this stage of the.
Yes, that's prior to this stage. Yes.
I understand.
So my segue into RTI actually came out when we started looking at kind of what, if you watch the registration program as it did things, what you would find, we said, well, actually, it makes a little bit of a deformation map. And we said, well, there's information there. Let's not throw it away. Now, we did in particular was, where's my thing? Okay. So what you're looking at is we took an infrared image from the 50s and compared it to one of the modern images that we took. So we're looking at, this thing was probably imaged in like 52, 53. This image was taken like 2000, when did they start? 2011. So there's all that time in between. And we took the two images and we registered them using the same methodology. And then we recorded the motion of the pixels because it had to, again, we let it elastically deform. And to see how much it had moved in the intervening time period. Where is this thing again? Oh, you know, it doesn't show up on the screen. That's very, I can only see it here. That's why I was, and there's a ruler on the original image. So we're able to turn this into actual pixel mode in XY. If there's piston in and out of the page, we're not going to see it. And you'll see that it is really quite elastic, right? It doesn't move very much here. It moves a lot here, and it's moving on the order of 0.5 millimeter. And so from the conservation standpoint, we said, well, you know, we want to look also at the physical nature, right? There's other stuff that goes on. Parchment in particular, you know, expands, it contracts, it gelatinizes, it delaminates, all kinds of things go wrong with it physically. So that's kind of why we started thinking about using RTI and other methodologies to look at other conservation aspects, which is how I met Dale, in fact. And I'm running out of time, so let me do this very quickly. And so what I said was, you know, you need some algorithmic definition. You need something you can implement in software. People have sort of poked at this a little bit by doing it by eye and by hand, but that just doesn't let you develop a real methodology you can apply an industrial crank to. And in our case, we do all this in PCA space, and so then we started thinking about RTI in 3D. And we said, well, what would be changing? And that's what Greg Williamson's going to talk about. And we said, well, it'd be the normals, because that's what you get out of that particular thing. So that would be sensitive to changes in the actual object itself, rather than just the surface, because we only see the projection on the surface when we take the spectral images. And actually, should I skip this? It's
just briefly talk about the fundamental idea of calibrating a mobile phone.
Okay, so very briefly, so one of the ideas that myself and a colleague had was to think about crowdsourcing data for mostly built heritage, outdoor monuments, statues, historical buildings, excavated archaeological sites. And the idea was to get enough finely grained data through crowdsourcing that you could figure out a way to turn this into these data sets you can extract information out of. So we started thinking about mobile phones, and so it's crowdsourced, tourist-based data, apps, all that social media stuff that a lot of people like. And so the question is, well, how good are the cameras? So we started to take a quantitative look at these cell phone cameras and think, do they measure anything well enough that we could actually get any real data from them? And HistoryPin is actually an existing phone app that we're working at. They provide historical images. It's available on both Android and Mac. You can take a look at it. It's kind of fun, actually. And so what we did was, in order to make this work, when we take these images, we need to have a color target. We need to have something Well, the cell phones by themselves are just sRGB, and every single cell phone vendor is completely different. And it turns out that they actually saturate the hell out of most colors. And unless you do a lot of work, they're really not very quantitative because they're meant to be nice looking for our eyes. So what we did was, so these are actually, there are very robust color standards that one can use outside. So it's not a hopeless task because you can't put this outside, but you can put ceramic tiles outside. So what we did was we measured a bunch of Great Tape Macbeth color targets. We did a little pilot project at Harvey Mudd College with, so here's our quick response, this is our social media aspect to see how many hits we got on a campus of about 1,000 people. And these are the color targets. And so we did this, we wrote some code, but we used mostly some commercial software from Imatest, which is a widely used by a lot of color people that review cameras and do color metrology. So Norm Corin actually gave me a couple licenses for it. So we measured LAB, did the usual stuff. And so the answer is that actually we get these numbers for changes in L that you can measure. And in other words, you can, this is the errors that they get against the Great Tape Macbeth charts. And if you look at values in the literature where people have measured using various colorimeters and spectrophotometers and all kinds of things, changes in cultural heritage, where is this? There it is again, please. You see numbers for delta B and delta L that are actually certainly on the order of or larger than what we get out of these phones. So at least at a first pass, it suggests that the phones are useful and they're only going to get better. And when they have 12-bit raw data on a cell phone, then we're really good, because that we know how to work with, because it won't be blown out and saturated the way all the data is. So again, it's another example. You just have to calibrate and see if it's going to work out. It could have easily turned out the phones are no good, but we think that they're good enough, and in a few years they'll be better.
How you doing?
All right. I'm sorry I went 5 minutes over.
That's all right. We had questions, which was absolutely fine.
How do we get out of here?
So what we're going to do is we're going to try and give you an idea of each of the panelists' work in quant imaging. And so John Delaney is going next. John is the Chief Imaging Scientist at the National Gallery of Art. There we go.
So I'm going to actually talk about examples of novel image products that have been obtained from imaging tools that we've been playing around with and kind of developing and applying them to data from various imaging modalities. And the idea of imaging modalities is we don't all just take color images, we take X-ray images, and there's now such a thing as macro X-ray fluorescence images as well. So where does this sort of fit into this big issue of the entire, museum-based computer processing network type environment? And basically, there's two levels. There's the end products that go to users, which could be actually images themselves, or it could actually be data information, right? And there's a visualization layer, which is a series of displayers that you could be used that are customized. And what ties this all together is a semantic layer, which links into to all the data via the metadata and content-specific information. And that sits above a bunch of things like text mining tools and analytics that would look at conservation art imagery, that's conservation space type things, or specialized image processing tools that are being developed by various groups that are looking at analytical data. And one of the key things in there is this metadata, which allows you to actually do the searching and find the relationships. So what I'm going to focus in is on the special processing tools and some of the analytical data and what comes out of that. And I'm going to focus on image registration tools, the enhanced tools that provide enhanced infrared reflectograms, and third, tools that provide mapping and identification of artist materials in situ. So the registration problem is kind of systemic throughout everything one does when one wants to compare two sets of images. The problem has been talked about earlier about change detection over time. It can be also what is the relationship between what I see on the surface of the painting, what's below, how do I compare two different paintings. And so the task that we took was to look and say, why don't we come up with a tool that will register any set of images with any modality to our common reference image? And that is because we don't have any coordinate systems that are encoded in the metadata. So we take the color image, which is usually the highest quality image and the one that everybody's got a copy of, and we register everything against it. Now, part of the trick is the imaging modalities that we use often don't have the same content. If you look in the X-ray or the infrared, there are things missing or new things appear. So we spend a lot of time looking at the spatial dimension, the spatial scale you want to do correlations over. And this tool set allows us to do mosaicing, allows us to look with multiple and hyperspectral images, and do this in a automatic fashion. And it's a multi-threaded tool, and it's a GUI based, so it can be run by conservators. Now I'll show you an example of an output of this. This is a project going on in the gallery. This is a painting by Vermeer. That's the color image from Alan's group. This is the infrared, which is a composite infrared, registered to the color image very accurately so that at the crack level everything's perfectly aligned. And you can see there's a lot of differences between those two pictures. So they don't just register just on the content. We do the X-ray as well. And then you can then look at merging the X-ray with the IR, which obviously showed that hat underneath, and come up with this picture that has the information about the face below and then the information about the hat, and put that together. And it's rotated, yes, right. Okay? That makes sense? Clear enough? Okay. Now, in order to do this, what type of equipment do you need? What we found is that you need to operate at very high resolution, typically 300 or as much as 500 dpi for the infrared scanned infrared reflectograms, and also for the X-rays themselves, and also for the color images, because you need to look at the texture of the paint, you need to look at cracks, because those are the features that stay in all the imaging modalities. So we have a high accuracy color computerized easel to essentially allow us to do the mosaicing, and we can capture some astronomical rate, about over 1,000 images per hour, and then post-processing allows us to register with the high-resolution color images. Now, of course, one of the things that have been going on with conservators is to take images in different spectral bands, and here I'm showing you a detail of this painting collected in different bands as you go further into the infrared that reveals better the drawing, the initial drawing that shows the Madonna and Christ in intimate, they're basically, their faces are close together, which is very different than the more traditional view. But the trick is that if you start now applying math models and actually start to do some image processing and try to model the paint layer of lead white, as you can see in the picture outlined in yellow, you get a much better view of the drawing underneath. So we've taken all of this multispectral infrared image and use it not just to find the best spectral band to look at, but to take all the data to try to model and remove the paint layers more effectively. Okay? Yes?
What sort of IR filter are you using for that?
We're using, in this case, the camera system is sensitive from 1,000 to 2,500 nanometers, and so we use a series of astronomical filters that are optimized for transparency in the window, atmospheric window. That's the cheapest ones to get, other than ordering custom ones.
And this modeling is a very sophisticated form of some form of
It's Kabelka-Munk.
subtract.
Yes, it's a Kabelka-Munk model, relatively straightforward. It's an approximation. You're using one of the images like J here, which is closer to the visible, as your reference image, and you're applying it to, let's say, image K, and removing the contributions of J from K in the Kabelka space. And what you're revealing, of course, is the more of the drawing below. And those parameters change where you look. Because the paint layer is changing in thickness and the absorbing properties of the paint's changed, it's not surprising we have to kind of do something where we look around at different places. This is another example. At the gallery, you can see the feet shown in yellow of a drawing as I flip the infrared of this picture. Oh, thank you. So there is some drawing. Try not to blind Greg here. Underneath here, with the characters flipped, there are some faces here that you can't make out. If we look at one of them, we can see there's a face underneath this poor guy's legs, and we can see that, but we don't see enough detail. Doing another transformation technique using all the spectral data, we can get enough of information that's useful for a conservator. Now that's using that's processing with a limited number of bands, but you can actually look at the data in the spectral domain as well. This is an overall mosaic of an impressionist painting. That's sort of the classic infrared. You can see there are some changes, like in the shapes here in the background, such as the chairs. You can see the position of the eye. But the moment we put it in this false color space, it'll make an art historian gasp. The conservator can see the dog here and can see more of the changes in the room, and also start to get an idea of the material changes. Different paints are used, although visually it looks about the same. So not quantitative, in this case qualitative. We'll get to the quantitative part in a minute. And the quantitative part comes about actually doing what Greg mentioned. If you calibrate to reflectance, you can start looking at pigment and, we'll show you in a minute, paint binder identification and mapping. And the idea is, instead of just taking images in a couple of different imaging modalities or a couple of different spectral bands, to collect in a sufficient number of spectral bands to reproduce the reflectance spectra at a high enough detail and over a large enough range that you can get information that are related to the electronic transitions and actually overtones and vibrational features that are fingerprints for the materials. So in this case is an early Italian painting. We can see this is ultramarine blue on the knee. That's where I pulled the spectrum out of. But we get small features here, which the geophysicist will tell you is related to gypsum. That's the ground layer that you'd expect. So I'll show you some examples here of what we were able to pull out of an early Renaissance painting here by Cosimo Tura. These are 4 panel pieces, and we're going to look at just a couple of them. This is the end result of taking spectral data from 400 to 1700 nanometers and then doing some processing on it to pull out a basis set of spectra which describe the painting. They're shown here. And then from that we can query the cube and make a map of where they're coming from. And then we go back to our library of database of materials, and we could begin to identify what these pigments are or these paint mixtures are, and then cross-reference with other methods such as cross-sections or X-ray fluorescence. We also find things like the cobalt blue that was used to in-paint losses in the ultramarine blue, the ultramarine blue robe, and also in the azurite and the like. And here's our bands associated with the ground layer, the gypsum as well.
Wow, it's a lot of in paint.
Yeah, well, it's,
It's an old painting.
it's an old painting. Pushing further out at longer wavelengths, we're finding that you can get some information related to the organic materials, in the case of the binder itself. This is a detail here of the face of one of the characters here. This is Gabriel. This is the X-ray image. And the X-radiograph shows you that the face is relatively transparent. And it's only in the white highlights, a little blown out here, that you see the density of lead white being used. This is a map of actually focusing on binder-related materials. For egg yolk, for fatty acids, we see a specific band in the near IR, which we can use for mapping. And we can see that that band is only present where the ochre is and where the highlights are, which we know are in lead white, but not in areas of the rest of the face. We don't see that band. We see a characteristic of animal skin, or basically animal skin glue, which was used probably with chalk. And that's the way you'd want to paint this painting, because the high index of the egg would make the chalk appear transparent. So we're seeing the systematic use of egg uses versus animal skin glue in these different paints to make up this painting. Now this is, I've shown you on the small scale. You can do this type of technology and this type of measurements on the large scale. This is a painting by Pollock called Mural, which is 8 feet high and 19 feet long, which we collected hyperspectral data across the entire painting to get a map of the materials used. I'm only going to show you 3. One of them is actually a white house paint that happens to have basically kaolinite in it, so some sharp bands you can use to track it, and then 2 phthalo pigments, a green and a blue pigment that Pollock used. And if I go to the map now, you can see the red, which is the house paint, was used to push down some of the colors at the relatively late stage. It's a commissioned piece. Maybe he kind of ran out of expensive paint at that point. But the other thing is you can see that the phthalo blue pigments uses these dashes and strokes all have about the same brush size, which is of interest obviously to the conservators and how the thing was painted. So basically, getting towards the end of the talk, we're now moving into looking at another modality which has been made very popular and is a very powerful technique developed by Joris Dick and Company in the Netherlands, which is a macroscopic X-ray fluorescence mapping. And there's some initial results that we're getting with our system. So what I hope to show you is that there are a lot of things to do in terms of making these type of calibrated image products useful and collecting them, but it's possible to do that in a museum setting. Okay.
Great. John French is next. Yeah, go ahead, yes, absolutely. Some good stuff. John French is next. John is the Director of Visual Resources at the Yale University Art Gallery. And while
We're shifting gears a bit.
we're shifting gears a bit, because the last talk talked about mathematical transformations, being able to subtract some spectral values in order to enhance the information we can get out of that. There are obstacles in the culture of museums that might, not just mathematical problems we have to overcome, but cultural problems we have to overcome. John's going to talk about that.
My name's John French, and I work at the Yale Art Gallery. I'm going to talk about a project that was done between some of the conservation staff and Yale's computer science department. Part of this that began the drive was that Yale recently opened a new collaborative campus space where there was going to be shared conservation facilities, shared imaging facilities, and computer science and other sciences were going to move to that area. And Yale as an entity was looking for ways for groups to collaborate and see how these new interactions could work out. So our conservation department identified that they historically have various module means that they're trying to look at images, study and analyze objects, but often are then forced to have to look at them in a variety of various programs that they then have to learn how to operate. And there's no way to do easy comparative analysis within one interface. So a project was launched in 2011 where we wanted to look to see if we could identify a way to build a software program that would allow us to take images like these of historical documents, CAT scan imagery, normal photography, 3D modeling imagery, hyperspectral, and combine them all into one program where ideally you would be able to overlay data and do comparative analysis of one data set over another. As we've talked about some, we had this bust that you see on the bottom that is a plaster cast of which there are 3 known copies of, and the presumption is that the original was at Yale and other copies were elsewhere, and the hope was to scan each one of those and do some analysis of overlaying these objects to be able to see which one went in what order. The closest anybody really had at that point of doing comparative analysis that we were looking at was something like the Van Eyck project, where you could lay all of these various images in and click on and off and show them, but there was no way, again, to do comparison. This really became more of just a public educational tool to teach them. We were clearly looking for more. The file types that we were looking at working with and we traditionally work with varied from 2D to 3D. So we were looking for a way that the programmer could build something that would read all of these various file types, which the project ultimately was successful enough to be able to do that. The project was written as a grant. We were awarded a 1-year grant to the tune of $80,000, which covered the acquisition equipment. So we needed to get a hyperspectral camera system built. We got a next engine 3D engine scanner to do the modeling of some of the objects. and then some funds to cover 50% of the salary of the computer science person who was going to be writing and doing a lot of the capture. The art gallery agreed to provide the materials, 20% time of the conservation staff and myself to help enable the project, and all of that again would happen within a 1-year period through the grant. So looking here, you see what ended up being the end result product that came out of this. So we were able to build, not we, but the computer science Min Kim was able to build a product that does allow you to put all these various file types in and make some adjustments and do some readings within the project. The product, partly because of time and I think because of interest in computer science area where they wanted to go with the project versus the conservators, we don't have the means to overlay data to do that comparative analysis. So this is still a useful tool, or could be a useful tool, but the conservators really aren't using that much. I'm going to show you at the end a live demo or a QuickTime video of kind of this going through its paces versus running it right now. It's relatively processor intensive to run, so I don't want to risk that it crashes while we're in the middle of this. But the software has some basic interfaces where you can go in and open files through 2D directories and 3D directories. You can look at your 3D modeling, rendering, and various points of point clouds, wireframes, skinned, and such, and turn those on and off. You can do some measuring within those, so you can measure from point A to B and annotate that information. And then you can also bookmark some of the views so that if you get to a certain area that you really want to look at and share that later or look at it again later, you can pull that back up again. This is one of the tools that we actually did find useful at the gallery. We're lucky to be close to the hospital where we can actually do CAT scan imagery of some of our works. And this painting in particular, we were looking, if you go back a few slides here, the top row image, you can see those circular patterns up in the upper area, and through general inspection, we were able to tell that the thought was they were hollow underneath there. And the question became then, why were they hollow? So X-ray scanning was done to look and indeed show that there are voids under that space. It still doesn't tell us necessarily what they were for, but it does tell us there was nothing in there. So they can at least look at that, but also the surface changes with temperature, humidity can kind of be looked at and understood what's happening underneath over time on that. Additionally, we have tools built in here that allow you to read some of the numeric information coming off there, so you can start to do some beginning information ideas of pigment analysis. What we haven't built into the tool that would want it to go in the direction of was to try to build basically a database of pigments so that a conservator would be able to click on a point, get a reading, and then ideally compare that against a database of known pigment samples where somebody's actually taken a physical sample and run it through some of the chemistry that they do. Because the ideal goal is to be doing non-invasive conservation treatment. So if we could be doing this through visual analytics, it would be the ideal direction to go. Our movie is not going to play. I'm going to show them. You have it on your desktop, right?
Yeah.
Okay, I'll show that at the end of the presentation just to move through it. So at the end of 1 year, the project was completed enough that the funding agency was happy to see that it did what we said it would do. But again, it didn't fully meet the needs of our conservation staff who are still not fully adopting it themselves. What we're hoping to do is get this in the hands of more people to start working with, to give more feedback as to further direction. The product is up on SourceForge, which is publicly available, but it's not an area that a lot of people know. So where this project potentially failed in many ways was we didn't get a good means of getting it out into the public's hands and getting a sense of user feedback on this. There was a white paper written that deeply outlined it, but it was geared more toward the computer science industry versus the cultural heritage industry, who would have a big interest in this. There was look at presenting it at IS&T last year, but we ended up having to withdraw at the last minute because there actually became a conflict of interest that we learned at the last second. You couldn't present findings from one paper in the same conference of another, so we had to withdraw and not be able to present that information to an audience that might have been able to get that. So we're discussing whether we rework the paper entirely to make it unique enough to present this finding at something like IS&T, or we look for conferences like this or AIC that conservators often go to. The direction the software is going now is computer science is still very interested in it because they spent a lot of time on the coding end, and they found a new partner on campus to work with, which is the manuscripts department. They are now using this to start to do more of that pigment analysis where they can try to read spectral information, and they've started to build in tools that allow you to export that data so that it could be further analyzed. The group they're working with are more curator researchers than conservators, so it's up to the computer science people to be running this program versus the end user. So again, the project has kind of side-passed the audience that originally it was built to do, and I think the disconnect kind of became after we did the initial captures. The computer science people kind of just ran off to their labs and started building this without a lot of communication back with the original partners of, is it doing what you need? Do we need to readjust or not? So these collaborations are great, and it's a direction we want to see going, but I think we need to work on how the communication goes, and more so how we get it out into the community to get feedback into it and ideally get other people to develop it more. These are some of the original people involved in the programming end of it. Again, you can go to that website and download the current version and the manuals and the white paper. I also have copies with me here if people are interested, along with some data sets that you could actually load into the program to look at it if you didn't already have these file types.
Which website, John?
I'm sorry, what?
Which website?
The back here at SourceForge, you can go there and get, you can see all the varying documentation on it, and then you can also download the product itself directly from there.
Does that site include the sample files from
It does not include the sample file sets, and that's if you want to get a hold of me, I'll be happy to provide sample file sets so that people could have something to work with if they didn't already have something to at least to begin to look at.
Or if you've got a thumb drive, he'll give it to you.
If you have a thumb drive, I can give it to you here and now. I have the program in a zip file and such too, so if people are interested, I'm happy to share. There you go. All right, so here's moving through some of the CAT scan data. You can move, pivot and move. You can do measurements so you can get that information. With the 3D modeling, you can obviously move around. You can modulate the light source. You can turn wireframe on or off. And then in the hyperspectral area, you can point on the various images to get spectral data on that. So again, that was a very quick crash through. I do have it on my computer if people are interested in looking afterwards. I'm happy to pull it up live so you can look at it a little bit more. Thank you.
We're going to end the formal presentation with Greg Williamson. Greg is a software engineer. He worked with me at the George O'Keeffe Museum summer 2012 and is since now working and solving problems for IDEAM, the gestural and multi-touch table company in Corrales, New Mexico. Greg worked with me directly to try and solve some of the quantitative problems surrounding reflectance transformation imaging, and that's what he's going to talk about today. There you go.
Thank you, Dale. Before I start, can we take a quick poll? How many people have actually made an RTI and done a capture sequence? You? Okay. How many people know what an RTI is but just haven't done a capture sequence yet? Okay, good. That just gives me some background as to how much details y'all need. So, like Dale said, summer 2012, the Georgia O'Keeffe sponsored a 12-week research project where we set out to see if reflectance transformation imaging was a viable digital imaging technique for monitoring changes in artwork or other cultural heritage objects. We also did photogrammetry to see if that was also a viable technique that could be used in the conservator's workflow. It was a 2-week boot camp in how to do capture sequences and how to process the image files, what data is actually in the image file, and everything there is to know about RTI. It was a really successful research project. We made some really great gains in understanding in the capture sequence. We documented everything in O'Keeffe Imaging Project at .wordpress.com. At WordPress.com, and you can see tutorials on RTI. All of our documentation is there. Really great metadata on the research. And we discovered, yes, it's really a great method that a conservator could possibly use to integrate into their workflow for monitoring change, but the next step was to really pin down the data and make it quantitative and say, yes, here is the change, and capture that. And so through Dale's meeting with Greg, they said, well, the first step is to do the precision, to figure out the precision. If I take the same capture sequence 3 or 4 times, am I going to get similar results? Dale got back in touch with me and said, well, hey, would you like to be part of this imaging project? And I said, absolutely, it'd be a great chance to work with these guys to try and further this research. Here's an example of a RTI that we did in infrared, and I think it's a PTM at the end of that. That's Georgia O'Keeffe feather and horn. So what is it that we're looking for in precision? What is it that we're measuring? I think that needs to be cleared up, and that is the surface normal. Okay, so the surface normal is just the imaginary line that is perpendicular to a tangent plane of an object. So it's just pointing straight up from a surface. Okay, and that's what RTI gives us. So reflectance transformation imaging is a digital imaging technique where you take a stationary camera, stationary piece of art, and you change the light source. And that gives you lots of different reflectance values. And you put it into the software, and the software not only gives you RGB data at every pixel, but there's also more information. There's also the surface normal data. It tells you which way the surface is facing. So that's really valuable information for tracking possible changes in the surface. Oh, hey, it's facing this way in January and this way in June, to coin Greg's phrase. And
It's going to go viral in a second.
it will. Then we can track change over time. So I was really happy to be part of the project. So first we had to establish a ground truth of a series of RTI captures. So what we did is, you'll see it later, I drew a very exciting painting with pastels and crayons. It's beautiful. It really reflects my artistic talent. We put it in the easel, we set up the camera, and then we did 5 back-to-back capture sequences. So we tried to minimize all change. The painting was fixed, the camera was fixed. We tried to, Dale can speak on this further later, but we altered the capture sequence to really minimize the different positions of the flash. When you have to do an RTI, you have to take you have to change the light source 60 different times. And so we tried to really be precise in where those positions were over the course of 5 capture sequences. We tried to use the same ambient lighting, and we tried to use the same power from the flash. Those settings were kept the same. We used the exact same camera, same flash, same batteries, which can be a problem. And the result is we got 5 surface normals at every pixel along with the RGB data. Okay. So what can we do with that data? Well, once we have the surface normal information embedded in these RTIs, this is where I came in. They said, well, hey, we have these RTI files, but they're in binary. We need someone to parse this binary and extract the data, give us the actual surface normal values. And that way we can calculate mean, standard deviation, and we can really see how much noise or how much change these surface normals have. We can look at a small area and say, okay, the surface normals are pretty much the same. Good, we're good to go. So I don't know if anyone's ever opened up an RTI file and looked at it, but it's just a bunch of squiggly lines and spoons and magic. It's binary. And so you either learn to read binary or you learn how to parse the file, which I was glad to be
The
useful
second
in that.
option is much better.
Yeah. So there's a standardized RTI file format. I have it with me if you'd like it. Give it to you on the thumb drive, or you can just look it up online. And it tells you exactly what the file format is going to be, what the header says, what the information gives you. So I just went through and wrote a script in Python that parsed these RTI files and then got to the main data and extracted surface normal data. So each pixel, actually we disregarded the RGB value and we just focused on the surface normals. The surface normals, you can see they're just these imaginary lines that are shooting up from the painting. We put those in Cartesian coordinates. So if you picture a half dome, there's an X, a Y, and a Z, and that represents from the origin what path that vector is going to take. So we ended up with 3 different files, a file full of X values that had the same coordinate system as the painting, Y values, and Z values. This doesn't have the missing slide. Okay. So what we did is we took a small region of interest, the same region, because the RTIs were taken back to back and nothing moved. We were able to just crop a little tiny region of interest on all 5 of them and analyze those and calculate the standard deviation, calculate the mean. And we define variability as 100 times the standard deviation divided by the mean, and that gives us a good indication of the precision. And we discovered that, great, the RTI method has a really low percentage, which indicates a high precision, much more significant over the PTMs that we did. You can notice there's a lot of variability in the PTMs and that the RTIs are superior in precision. So I think Dale and Greg decided that anything below 5% was a go for tracking meaningful change. And so getting less than 2% was a really happy result. So now we know that we can go back, we can look at the same pixel over time, and if it's within the red circle and it's just changed a little bit, we can say, oh, that's maybe the temperature or photons bouncing off of it. It's just changed a little bit.
Or it's the variation just in the capture sequence.
Right, nothing to be worried about. No one stuck their finger through the painting and ruined it completely. However, since we have a ground truth, right. Now that we've established this ground truth through this series of RTIs, we know, however, if the surface normal is outside that range of statistical control, then that might be an indication of something of surface change that might need to be monitored, or for Dale to step in and say, well, what's going on here with this painting? And so it was a successful short run of research to establish the precision in the RTI methodology, but we're now kind of at an impasse. We've said, okay, yes, it's precise. Now what? How do we make it quantitative and put it into the conservator's workflow so that he or she can use it to track topological changes? So you've already heard from 2 different people that registration is a big problem. Whenever you have something taken in January and something taken in June, there might be a slight change in the tip, in the tilt, maybe even a different camera is used, who knows. But once those RTIs are taken, they need to be morphed and changed so that they're registered. But not only the color data has to be accounted for, but the X, the Y, and the Z, and the surface normal has to be accounted for too. And that's a current problem that we're trying to solve and reaching out to various people to help us with that problem. In doing this research, we found some really great methods for minimizing the human error in the capture. For those in the room who have made an RTI, you know that there's a part in the RTI building process where you have to take a little round circle and you have to center it around a sphere. And that's subject to error, just it's someone eyeing it. The software tries to help you out, and it does a Huff transform, and it tries to localize the sphere, but there's a chance that in one capture sequence, someone centered the sphere here and another was different. So there is a need to minimize the human error in the capture sequence so that you can get quantitative data out. There's also a new method Dale developed where you can minimize the change in the lighting sequence, so you can use the exact same lighting sequence every time so that the change in light isn't significant enough to ruin the data. And this minimization in human error most of it can be done in automation in software. Some of it is just education, learning the proper techniques for RTI capture sequences. Calibration, if we're going to get meaningful Z value, we're looking at the surface normals, and we're looking at which way the surface is facing, but we're not necessarily getting 3D data out of it. I know that the surface is facing this way, but I don't know how much it's extruded. And there's instrumentation peripherals that can be used that can help us extract that data from the RTI. We need to understand scale. We need to be able to track a change that happens within a 10 pixel range, or if the painting is just bent in half. And you take the scale out to a certain degree and you say, well, these pixels on this side of the painting are completely different than this side of the painting, and that's meaningful change. But if we're just looking at the local, there might not be enough meaningful change to see a bent painting. So understanding scale and how the software can be used to account for that is important. And then whether we are getting a true deformation, or in the registration technique that we decide to use, there's some type of anomaly there.
Thank you, everybody.
Thanks.
Thank you.